Okay, so we have a glucose solution that's administered intravenously into a bloodstream at a constant rate of R. As the glucose is added, it is converted into substance and removed from the bloodstream at a rate of proportional to the concentration at the time. Thus, a model for concentration is, okay, so it's introduction and removal. That's the rate of change. Okay, that's the rate of change. Suppose that the concentration at time t is C0. Determine the concentration at any time t by solving differential equation. Okay. So what we have to do here, we have dc here. There's no way for us to bring this c, okay, to the other side unless you bring the whole thing. So divide both sides equally by r minus kc, and you get one left here, and you multiply that by dt. This is going to be ln of r minus kc times by a -1, right? Because c is the variable here, and here you get t plus some constant. Let's call it d, because we already used the letter c here. So then ln of r minus kc is equal to minus t minus d. Okay, before we plug in the initial value, let's do this. Let's convert it to exponential form. So you get e to the power of minus t minus d, okay, which is the same as e to the power of minus t over e to the power of d, right? Okay, so that's the same thing as 1 over e to the power of t e to the power of d. All right, so we have then minus kc is equal to 1 over e to the power of t e to the power of d minus r. Then kc is equal to, divide both sides by the minus k, and we get rk minus 1 over k e to the power of t e to the power of d. So finally, we've taken care of that already. So that's our c as a function of, okay, c as a function of t. So now in here, let's plug in t is equal to 0. So we get c0 is equal to r over k minus 1 over, if you set that equal to 0, you just get 1. So k e to the power of d. Now our goal is to actually isolate for this d. All right, so let's subtract c0 minus rk. And right after that, we're going to multiply both sides by negative. So we actually get this. Okay, so that's same as e to the power of minus d over k is equal to r over k. Okay, multiply both sides by k. Okay, and we ln both sides. You get minus d is equal to the ln of r minus kc0. Okay, that means d is equal to minus ln of r minus kc0. Replace that in here. So what is e to the power of minus ln of r minus kc0? Okay, you just bring this negative up, then you get this. But because the base is the same here, e and e, this is equal to r minus kc0 to the power of -1, which is same as 1 over r minus kc0. Okay, so what that means, okay, all the way bringing it back here, we get c is equal to r over k minus, okay, so this will become 1 over this. So it's the same thing as r minus k c0 on the top, k e to the power of t. Okay, maybe I should put that at the front here because this is a variable, e to the power minus t, and this is all constant here. Okay, constant. And we can even combine these two. So you get r minus r. So you actually get kc0 over k e to the power minus t. That gets reduced, so we get c is c0 e to the power minus t. Well, it simplifies quite a bit, doesn't it? Now the part B is what happens as t approaches infinity with this. Well, clearly that's more obvious if we put it this way. So as t approaches infinity, right? We have some constant divided by infinity. So this is approaching, right? It's approaching 0 as t approaches to infinity. Goes forever, it's approaching the concentration of 0.